Welcome back to Josh Does Math. In this video, I'm going to be using implicit differentiation to solve for dy dx. So here's my implicitly defined function right here, and I'm going to do a little bit of rewriting before I even take any derivatives. I'm going to make this x to the negative 1 plus y to the negative 1 is equal to 1, because that's going to make my next step a lot easier because it's going to turn those quotients into simple terms that I can use the power rule on. And now I take the derivative of both sides. The derivative of the first term here is just going to be the power rule. Power out front, 1 smaller on the power, plus. Now I'm taking the derivative of this right here. So I'm going to write this as dy to the negative 1 dy times dy dx. That is just using the chain rule. And I didn't take any derivatives yet, I just set it up so that I set it up using the chain rule so I can easily take the derivatives in the next step. And that's going to be equal to the derivative of 1 with respect to x. Okay, that's 0. There we go. So now I can rewrite this. I'm going to write negative 1 over x squared plus this right here. Once again, I'm using the power rule. Power out front, 1 smaller on the power. It's going to be negative 1 over y squared, just like what we did with this term right here, times dy dx is equal to 0. Well, how about if we add 1 over x squared to each side? We can do that. And how about if I multiply each side by negative 1 over y squared? So I multiply each side by negative y squared. I get negative y squared all over x squared is equal to dy dx. So that's how you do implicit differentiation. I set it up so it would be a lot easier later on and I wouldn't need to use the quotient rule at all. But I didn't need to do that. I could have used the quotient rule, just that made it simpler. Then I implicitly took the derivative of the whole thing, and then I just solved for dy dx, and that's all there is. Thanks for watching.